Hello everyone. Today we study the maxima and minima of multivariate functions. First, we give the definitions of global maximum, minimum, and extreme value of function. Let f be function with domain S, and let P0 be a point in S. If fp0 is less or equal to fp for all p on S, then fp0 is a global maximum value of f on S. If fp0 is larger or equal to fp for all p on S, then fp0 is a global minimum value of f on S. If fp0 is either a global maximum value or global minimum value of f on S, then fp0 is a global extreme value of f on S. In the definitions in 1 and 2, if we require only that the inequalities hold on some neighborhood of p0, then we will have the definitions for local maximum value and local minimum value. And if fp0 is either a local maximum value or a local minimum value of f on S, then fp0 is a local extreme value of f on S. How to judge whether the function has an extreme value? It is easy to judge in simple cases, such as this equation, z equals 3x squared plus 4y squared, which represents an elliptic paraboloid surface. According to the figure and the definition of extreme value, z has local minimum value at 0, 0, and z 0, 0 is also a global minimum value. Another example, if z is this function, the figure of it is a lower half conical surface. Similarly, z has local maximum value at 0, 0. For functions z equals xy, it is a saddle surface. In some neighborhood of 0, 0, some functional values are larger and some are less than f0, 0. So z has not the extreme value at this point. Then when a function has extreme value at some point, here we give the existence conditions, the max minimum existence theorem. If f is continuous on closed bounded set S, then f attains both a global maximum value and a global minimum value there. Next, we give the necessary conditions of extreme value, the critical point theorem. Let f be defined on a set containing p0. If fp0 is an extreme value, then p0 must be a critical point. That is, either p0 is a boundary point of S, or a stationary point of F, or a singular point of F. Example 1. If fxy is this equation, from the inequalities below, f10 is actually a global minimum for f. There are no local maximum values. Example 2. Find the local minimum or maximum values of the following function. Solution. Since the function has no singular points, and the only stationary point is the point 0, 0, it is neither a maximum nor minimum point. So the given function has no local extrema. According to the existence of extreme value theorem, for continuous function on some closed and bounded sets, the extreme point is either boundary points or stationary points or singular points. If fxy has partials, the extreme point is stationary point 2, but the stationary point is not necessarily an extreme point. For example, we have proved before that for this function z equals xy, the point 0, 0 is a stationary point, but it has no extreme at this point. Then, how to judge whether a stationary point is an extreme point or not? The following is the principle. Second partial test. Suppose fxy has continuous second-order partials in a neighborhood of x0, 1, 0, and x0, 1, 0 is a stationary point, or the gradient of f at x0, y0 is 0 vector. Let A, B, C be the second-order partials and denote D as AC minus B squared. Then, if D is larger and A is less than 0, then f has local max value at x point, y point. If D and A are larger than 0, then f has local minimum value. And if D is less than 0, then f has no extreme value at this point. If D equals 0, f may not be extreme at this point. Example 3. Find the extreme values of this function. Solution. Let the partials be 0, and we get the stationary points 0, 0, and AA. Next, we compute the second-order partials AB and C as follows. At the point 0, 0, AC minus B squared equals minus 9A squared, and A is less than 0, so fxy has no extremum at 0, 0. Similarly, at the point AA, AC minus B squared equals 27 times A squared, which is larger than 0, and A is less than 0. So, fx has a local maximum value at this point. Its value is A cubed. Example 4. Find the minimum distance between the origin and the surface z squared equals x squared y plus 4. Solution. Let P, X, Y, Z be any points on the surface. Then we have z squared equals x squared plus 4. Substituting this equation in the term d squared to obtain d squared denoted by fx equals this term. Note f has no singular point. We just find its stationary points. Let fx and fy equal 0. We have the following equations. By eliminating y, we have the expressions below. So, the critical points are these 3 points. Furthermore, the second partial of fxy are the three terms, and d equals 4 plus 4y minus 4x squared. Since the value of capital D at these 2 points is minus 8, less than 0, neither of them is extreme. And the value of capital D at 0, 0 is 4, larger than 0, and fx 0, 0 is 2, larger than 0. So, the minimum value is f0, 0. Therefore, the minimum distance is the root of f0, 0 equaling 2. Now, we give a summary of the second partial test. For the stationary point px0, y0 of a bivariate function fxy, we can judge whether fp is an extreme value by the following second partials. Now, let's make a summary of this section. We learned the definitions of global and local maximum, minimum, and then discussed the max-mini existence theorem, critical point theorem, and the second partials test. That's all today. Thank you.